far as I can tell, we are live on voice. I can hear you guys look clearly. Can you hear me? Yes, I hear you loud and clear, Sally. Welcome and greetings. Apparently we don't yet have a video signal, so just let me shout as soon as you're ready. When you're ready, Sally. We spent the first couple of hours getting oriented to the station after the surge, which is tiny, very, very, very small. The station.
To determine mathematically the appropriate orbital velocity and period for the International Space Station. According to Newton's first law of motion, an object in motion will stay in motion unless an outside force acts on it. For satellites orbiting Earth, momentum and force of gravity have to come into play like a constant tug of war in order to balance the satellites within their orbits. If the momentum is too small, the object will be pulled down by gravity and hit the Earth's surface. Likewise, if the momentum is too great, the satellite will speed past the orbit and fly towards space. Once a satellite is traveling in orbit, it will lose momentum over time and will slowly spiral towards Earth if it is not boosted to the appropriate speed from time to time. For this reason, it is important to calculate and maintain a specific velocity and period. The formulae needed to calculate the necessary velocity and period are shown here. Where v is the velocity of the orbit, g is the gravitational constant, m is the mass of the satellite, r is the radius of the circular orbit from the center of the Earth, t is the period of the orbit, and f is the frequency of the orbit. The only tool needed is a calculator. Of course, the real satellite engineers tracking the space station use other satellites, telescopes, and computers. The International Space Station orbits Earth at an altitude of 350 kilometers above Earth's surface. We must determine the velocity needed by the International Space Station to maintain its orbit. The first step is to know what we were given. We have the gravitational constant, 6.67 times 10 to the power of negative 11 newtons per meter squared over kilogram squared. The mass of Earth, which is equal to 5.98 times 10 to the power of 24 kilograms. And the radius of Earth, which is equal to 6.38 times 10 to the power of 6 meters, as well as the height of the satellite, 350 kilometers, which is converted to 3.5 times 10 to the power of 5 meters. The equation we're going to use for this problem is the velocity of the orbit equal to the square root of g, the constant, times the mass, m, over r, the radius. Now that we have the given values and the equation, we are able to plug them in and calculate. We have the square root of 6.67 times 10 to the power of negative 11 times 5.98 times 10 to the power of 24 over 6.73 times 10 to the power of 6. By calculating those numbers, we get 7.698 times 10 to the power of 3 meters per second. This is the speed required to keep the International Space Station in orbit. The next step is to determine the orbital period of the International Space Station in minutes. The first part allowed us to determine the velocity, 7.698 times 10 to the power of 3 meters per second, and the radius was given in the original problem. To determine the period, we use the equation t equals 2 pi r over v. We are able to plug in the given numbers into the equation to give us 2 pi times 6.73 times 10 to the power of 6 over 7.698 times 10 to the power of 3. This calculation gives the period 92 minutes, which is the time it takes for the International Space Station to orbit the Earth. Objects that revolve around other larger bodies are called satellites. There are two different types of satellites: natural satellites like planets that rotate around the sun, and artificial satellites, which are human-made objects which generally circle around Earth or other astronomical phenomena collecting data. Two examples of human-made satellites are the RAD-ARSAT-1 and the RAD-ARSAT-2, both of which are Earth observation satellites designed to take images and data from orbit to help scientists track environmental changes and natural resources. They are responsible for monitoring and detecting oil spills, identifying ships at sea, watching ice movements, and observing natural disasters. The International Space Station is a special type of spacecraft that circles Earth in a lower orbit at about 28,164 kilometers per hour every 92 minutes or so. It serves as a laboratory and a home for astronauts and cosmonauts alike. Many countries around the world have collaborated to build and use the space station. The space station is critical to scientific research because it allows people to live in space every day, ever since the first crew members arrived in 2000. Research is done in the space station laboratories that could not be done anywhere else, much of which benefits people on Earth. For example, astronauts are able to observe the effects a microgravity environment can have on the body over the course of a long period of time. Orbits are repeating paths which objects, specifically satellites like the International Space Station, take around a bigger object, such as Earth. The height of the orbit, or the distance between the Earth's surface and the satellite, determines the speed and time it takes for a satellite to rotate around the Earth. There are three types of orbits surrounding Earth. The high Earth orbit, also known as geosynchronous, is 42,164 kilometers from the center of the Earth, or roughly 36,000 kilometers from the Earth's surface. At this height, the orbits of the satellites match Earth's rotation, and because they travel at the same speed, the satellites seem to stay in place over a specific longitude. However, they may go north or south. A satellite in high Earth orbit will seem to travel through the same point in the sky every 24 hours. To someone standing on Earth, a geostationary satellite will appear to remain in the same location in the sky at all times. Because of this, communication and weather satellites are launched into Earth's high orbit. Here they can constantly monitor weather and communication for a specific region at all times. Medium Earth orbits are closer to Earth than high Earth orbits, only 26,560 kilometers from the center of the Earth and approximately 20,200 kilometers above the surface. The closer to Earth a satellite is, the faster it moves. It takes 12 hours for a satellite at this height to complete an orbit, meaning that every 24 hours, the satellite crosses over the same two spots on the equator. The types of satellites usually found traveling in the middle Earth orbit are navigation and specialty satellites, used to inspect specific regions. The Global Positioning System places its satellites in a middle Earth orbit because it sees the same part of the surface every 12 hours, and it is very reliable. The low Earth orbit generally holds specific satellites and weather satellites about 644 to 1,610 kilometers above Earth's surface. Satellites in this orbit are responsible for day-to-day things, like transferring messages, emails, and videos around the world. Because it is the closest orbit to Earth, it is a highly inclined orbit, and it takes about 99 minutes for a satellite to orbit the Earth. The International Space Station is in a low Earth orbit because it takes less energy to launch the components into and sustain this orbit. The amount of energy needed to launch a satellite depends on the distance between the orbit and the location of the launch site. It takes the most energy to launch a satellite into high Earth orbit, as well as in highly inclined orbits. It takes more energy to launch an orbit into a polar orbit than it does to circle around the equator. As well, it is more accessible for crew and servicing. A satellite engineer is responsible for working and monitoring satellite systems, developing software programs, and collecting data and test systems. More specifically, a satellite engineer attempts to keep satellites functioning properly by designing programs to keep them in orbit. The position also requires that the person know how to create command systems that control satellite activities from the ground, detect any satellite problems, and collect useful data. In order to become a satellite engineer, most are required to get a bachelor's degree in electrical, mechanical, or aerospace engineering. In some cases, employees may even have to go as far as to get a master's degree. Satellite engineers are required to have well-trained computer skills, are able to write software programs, and have good written and verbal skills. It is also critical that satellite engineers be able to analyze and understand spacecraft subsystems, satellite communication systems, spacecraft operations, and ground control systems. A satellite engineer is a high-paying career because, as of 2015 in the United States, satellite engineers can make an average of $70,000 per year. An aerospace engineer, which is a specific type of satellite engineer, can earn as much as about $107,000 per year. All that is needed is a motive or interest in the career, and the time and dedication required to fulfill that goal. The following is an excerpt from an interview with Veronica Navarro, who is a system engineer with a satellite producer. She received a bachelor's degree in engineering and went on to get a master's degree in business administration and another in systems engineering. She speaks positively of the career she has chosen. For her, watching a satellite launch is like watching a movie. She enjoys being a part of a team, managing these complex technologies on a daily basis.
We have ignition and liftoff. Liftoff of an ILS Proton rocket from the Baikonur Cosmodrome in Kazakhstan, carrying the Nimiq 5 communications satellite.
My name is Veronica Navarro, and I'm an operations engineer. I had probably 2 teachers tell me that I'm good at math, and so maybe I should go into engineering. And I had no idea what engineering was, and I thought it was like a train conductor. I thought it would be like on the train, and I'd be wearing that cute striped hat. Well, I like Star Wars and Apollo 13 and all, so I was like, maybe aerospace sounds more interesting to me out of the options, which is like mechanical, civil, electrical. Space systems are out. We do satellite TV, like direct TV, and we do satellite radio, like for Sirius radio. We manufacture the satellites here, and I feel like I'm in the spotlight. I'm where all the action happens because I'm there when it launches. I make sure that it launches and it's in its correct parking spot, and then we give the satellite over to the customer and make sure that they're happy with it. So a typical day for me when I'm sitting on console, I'm actually going to sit there and monitor the entire spacecraft health. I'll wait for engineers to come and tell me if they have any updates, like if a temperature is going to be different than what they expected. I'll set alarms for them, and when it goes outside of the range that they thought was going to be okay, it'll alarm, and then I could let them know what's going on. Can you go ahead and sign this limit change request, please? Sure, no problem. We use a lot of computers, so I have my own personal computer as well as a workstation that consists of 4 computer monitors to monitor all the different subsystems. Power, the thermal, make sure everything, like the batteries are working and the heaters are working and nothing's getting overheated or get too cold.
Enjoy the ride.
I love the movie like Armageddon and Apollo 13, where it's like a room full of engineers. Every time we have a launch, I still get the chills. It's like watching a movie or something, like an exciting movie, and I'm watching it and it's happening real time. I love that when I could send a command to the satellite that's like 30,000 miles away, and I know it's gonna be up there like forever. Every time we launch a new satellite, there's new hardware, new tools that we're using, new ideas that have been implemented, and I like to see them at work and learn about them and then watch it like from down here.
Newton's observations, discoveries, and laws have revolutionized the way people think and pushed our understanding of science forward. Because of Newtonian physics, astronauts and physicists have been able to reach greater heights of understanding that eventually led to satellites orbiting Earth, assisting us to see a broader universe like never before. Satellites attempt to follow Newton's first law, stating that an object in motion will remain in motion until an outward force acts on it. This means that momentum and gravity both play a part in keeping a satellite from crashing into Earth. Too fast and it flies off into space. Too slow and it comes crashing down again. For these reasons, it is fundamental to use calculation and observations to ensure that satellites stay in their selected orbits.